Hello, and welcome to my presentation on Lab 2, Motion of a Falling Object. The purpose of this lab was to observe the motion of a falling object, create computational models of the object experiencing both the force of gravity and drag force, compare these computational models and the observational model, and finally to understand the effect of gravitational and drag force on a falling object. The main physics principle used for this lab was Newton's second law, or the momentum principle, which states that force is equal to the change in momentum per change in time, or F equals ma. The main physics equations were for the force of gravity, mg, force of drag, negative bv squared times v hat, Newton's second law, F equals ma, the velocity update, and the position update equations. Here is a preview of my results. There were 3 models made during this lab. The first was an observational model made via tracker, which included hand-plotted points to determine the change in position during each frame of the experimental video. Then there was the gravitational model, made with GlowScript code and predicted the object's expected motion using the velocity and position update equations, but only took into account the force of gravity. Finally, there was the drag force model, which was also made in GlowScript code and also predicted the object's expected motion using the velocity and position update equations, but it took into account both the force of gravity and the drag force acting on the object. For the experiment, there is first a recording, which was a frisbee being dropped from rest and falling to the ground. Then this video was uploaded to Tracker, and the calibrated distance traveled by the disc was to be 1 meter. Computations and initial values are the initial position being 0, 0, 0, the initial velocity being 0, 0, 0, delta t being 0.03, the mass of the disk being 0.175 kilograms, and the acceleration of gravity, small g, being negative 9.8 meters per second squared. Then computational models were made in GlowScript code to show the change of position with and without the drag force. Here is a video of the experiment. How exciting! The code for the gravitational model only took into account the effect of the force of gravity on the object. As seen, our initial position vector being 0, 0, 0, initial velocity vector being 0, 0, 0, delta t being 0.03, force acceleration due to gravity, mass of the object, force of gravity being mg, and while we are within our time frame, the force vector is just the force of gravity, and that ball velocity using the velocity update equation and the position update equation. And as delta t advances, then our position is tracked. For the drag force model, we have the same code for the force of gravity, as well as code to calculate the force of drag, which adjusts as velocity increases over time. And in this case, the F net will be the force of gravity plus the force of drag. Our results are as follows, with the tracker video and the drag force model video being quite similar, while the gravity model shows a much steeper acceleration due to gravity. Discussion. What does it mean? Terminal velocity is reached when a falling object has equal gravitational and drag forces, meaning that these forces balance the net force to 0 and halt the acceleration of the object. While none of the models presented show the disk reaching terminal velocity, it is still seen that the drag force slows down the object by counteracting the force of gravity. What if? If the object is initially thrown downward, it would have a greater terminal velocity than when it was dropped from rest. This is due to there being an initial force added alongside the force of gravity, causing drag force to increase to a greater magnitude to match the new downward force. In conclusion, this lab showcased the effect and importance of both drag and gravitational forces on a falling object, and how each of these forces can be calculated and iterated upon using Newtonian principles. Thank you for watching.